Hello friends, I am your course teacher Professor A.B. Shikalgar. In previous lecture we have seen the Kleen's theorem. So after the Kleen's theorem in our syllabus, the next point is the minimal finite automata. So first we will see what is the meaning of minimal finite automata. So finite automata, it can consist of number of states, okay, and the minimal finite automata means whatever the number of states are there, you are going to reduce that number of states, okay. So but here the reduced number of state finite automata, the meaning should not be changed. Suppose here one example is given, that is my deterministic finite automata in which 5 states are there, 1, 2, 3, 4, 5. Okay. So 5 states are there and we are going to reduce the number of states from 5 to 4, 3 or 2. Okay. But here whatever the finite automata we are going to obtain, that finite automata should accept all those strings which the exactly original finite automata should accept. Means the meaning of the language should not be changed, only we are going to reduce the number of states. Okay. So here how to solve the problems on minimal finite automata. The question will be like this: minimize the following deterministic finite automata, and one kind of finite automata is given. So here one DFA is given and the question is to minimize the finite automata. Okay. So how to solve those problems? There are 2 steps to solve those problems. Step number 1 is to check reachability of all the states. So here we are going to check which states are reachable states from the initial. Okay. So here which is our initial state? Q0. So what is the meaning of the reachable state? So accept our initial state, the remaining states are reachable from the original initial state or not. So here how we are going to check? Q1. So Q1 is reachable from initial? Yes, directly here arrow is given, means Q1 is reachable from initial state. Q2, yes, Q2 is also reachable from the initial state. What about Q3? So Q3 is reachable from initial, but here from Q0 to Q1 and then Q1 to Q3. It is like this. Then what about the acceptance state, which is Q4? So Q4 is reachable, here it is, from Q0 to Q1, Q1 to Q3 and Q3 to Q4. Means here in that particular diagram, all the states are reachable from the initial state. So here in some of the diagrams, it may be like this: any of the state is not reachable from the initial state, then what we are going to do? We are directly removing that state from the particular transition table. Okay. So here in that diagram, all the states are reachable, so there is no necessity of removing any of the state in step number 1. Okay. So here it is clear, the reachable state. Then we are moving towards the next step, which is step number 2. So what we are going to do in step number 2? We are going to design the transition table of the particular DFA. Okay. So here transition table. Delta is the states, means Q0, Q1, Q2, Q3 and Q4. These are the states which we are going to write under the delta, and which are the input alphabets here? A and B. So those input alphabets I am writing over here, and that is particularly my transition table. Okay. So we will start with the Q0. So Q0 to A, where it goes? So that particular values we are going to enter in that particular transition table. So Q0 to A, it goes to Q1. So right here Q1. Q0 to B, it goes to Q2. So here it is Q2. Then which is my next state? Q1. Q1, Q1 to A, it goes to Q1 itself. Q1 to B, it goes to Q3. The next state is Q2. Q2 to A, it goes to Q1 and Q2 to B. So here it is Q2 and Q2 to B, it goes to Q2 itself. The next state is the Q3. Q3 to A, it goes to Q1 and Q3 to B, it goes to Q4. So as in that particular diagram, I have given it in the red pen. So it is important for us because all the equivalency depends on your acceptance state. So here write down the acceptance state Q4. The next state is the Q4 acceptance state. So what about the A and B of the acceptance state? So from Q4, the A goes to Q1 and the B goes to Q2. So that is my transition table. Okay. So in the previous step, that is in step number 1, we have seen the reachable state. And what I have told you, so if some of the state is not reachable, so here what happened, all the 4 states are reachable from initial state. So there is no necessity of removal of this state. Okay. So if any of these states, suppose I can consider the Q2 is not reachable. Okay. So if the Q2 is not reachable, then we are going to remove that state, means in the transition table also we are not writing that particular state Q2. So here it is not for that particular problem, but if some of the problems there will be possibility that some of the state will be not reachable, so we are removing that state from the transition table. Okay. So from that transition table, the next part is to find the equivalency. So here it is the zero equivalent. Okay. Zero equivalent means what? We already knows that there are 2 parts of this state. The one part is the non-acceptance state and the one part is the acceptance state. So in our DFA, which are non-acceptance state? Q0, Q1, Q2, Q3. These are non-acceptance. And Q4 is the acceptance state. Okay. So in zero equivalent, we are going to make 2 groups. The one group is of the non-acceptance state and the another group is of the acceptance state. So here Q0, Q1, Q2, Q3, those 3 states are the non-acceptance state, and then I am writing Q4, which is the acceptance state. Then we are going to find one equivalent. So the students listen carefully how to find the one equivalent, because it is some of the complicated part. If you can understood how to find the one equivalent, then you can easily solve the problems on the minimization of the finite automata. Okay. So how to find the one equivalent? So one equivalent means we are going to find step by step. Suppose 2 states we can consider, Q0 and Q1. Okay. So Q0 and Q1, these 2 states are still present in one group or not, that we are going to check. So how to check that particular? So which 2 states I told you? Q0 and Q1. Okay. So Q0 and Q1 on input A, where it goes? It goes to Q1 and Q1, means it is one state only. What I want? Q0 to A, Q1 to A. Here what I obtained, that should be present in one group in zero equivalent. So here it is the only one symbol, means obviously that will be present in one group. So here it is the Q0 and Q1, the input alphabet A, it goes to one group only. Then Q0 on B and Q1 on B. So Q0 on B, it goes to Q2 and Q1 on B, it goes to Q3. So now what I am going to find? Whether Q2 and Q3 are present in one group in 0 equivalent. So here it is the Q2 and here it is the Q3. Means these two states are present in one group. Therefore, what is the conclusion here? Q0 and Q1 are still in one group in one equivalent. So here I can write Q0, Q1, these are in one group. Then which is my next state? Q2. So what we are going to find now? Q2 is present with Q0 and Q1, or whether the Q2 will make its another group. Okay, so here Q2, so we can check Q2 with any of that particular state. So if Q2 is equivalent with Q0, then ultimately it is equivalent with Q1. Okay, so we can check with any one of these two. So now Q0 and Q2 we are going to check. So Q0 on input A, where it goes? Q1, and Q2 on input A, where it goes? Q1. Means now what? Again the same symbol, means it should be present in same group. Therefore Q0 and Q2 on input A, it goes to in one group. The next is Q0 on B, it goes to Q2, Q2 on B, it goes to Q2. Means here it is again the same state it can go. Therefore still Q2 remains in the group which contain Q0 and Q1. Then what we will going to check now? The remaining symbol, which is Q3. Okay, so Q3, whether it is equivalent with these three or Q3 will be making separate group, we are going to check. So we can check with any one of that particular. So I can consider Q3 to check with the Q2. Okay, so Q2 on A, it goes to Q1. So here it is the Q1, and Q3 on A, it goes to Q1. Okay, so here again the same symbol, means it will be present in one group. See here Q2 on B, it goes to Q2, and Q3 on B, what here we obtain? Q4. And here we can see the red pen and the double circle means the acceptance state, means Q2 and Q4, these two symbols are not present in one group in 0 equivalent. We can easily check here Q2 and Q4. So Q2 is present in that group of the non-acceptance state, and Q4 is present in another group of the acceptance state. So what is conclusion here? The Q3 is not present in the particular group in one equivalent. Okay, so here we are making another group of Q3 because it is not equivalent to that particular states, and as it is our acceptance group, that is the Q4. Then what we are going to do, the next is we are finding two equivalent. Okay, the same step we are going to continue, but what we have did in one, while finding one equivalent, what we check whether the symbols are in one group in 0 equivalent. So while finding the two equivalent, what we are going to check, suppose we find the whatever the symbols that are in one group or not in one equivalent. So when finding two equivalent, we only consider one equivalent. When we move towards the three equivalent, we can only consider the two equivalent. Then Q0 initial state. So Q1 is equivalent with Q0 or not in two equivalent, we are going to check. So Q0 and Q1 on input A, it goes to, we can see here the Q1. As it is the one symbol, it can be present in one group. See here, what happened here? Q0 on B, it goes to Q2, and Q1 on B, it goes to Q3. So Q3 is present in another group in one equivalent. So Q2 and Q3, Q2 is present in one group. Here we are only considering one equivalent. So Q2 is present in one group, and Q3 is present in another group. So what does it means? So in two equivalent, Q0 and Q1 are not presenting in one group. So here we are not making one group of Q0 and Q1. So we can write here Q1 at side and we move towards the Q2. So Q2 first we will find with the Q0. So Q2 and Q0 are equivalent or not? If it is equivalent, we are making one group of Q0 and Q2. So if it is not equivalent with Q0, then we can check Q2 with the Q1. So whether these two are equivalent. Then if it is equivalent, then we can make one group of Q1 and Q2. So let us check Q2 and Q0. So Q0 and Q2. So Q0 on input A, it goes to Q1. Q2 on input A, it goes to Q1. Means both the symbols are same, Q1 and Q1. Means obviously that will be present in one group. Q0 on input B, it goes to Q2. And Q2 on input B, again it goes to Q2. Means the same symbol making the same group. So Q0 and Q2 are in one group in two equivalent. So what about Q1? Now there is no necessity of finding whether Q1 is equivalent with Q2. Okay. So Q1 we are making the separate group and Q3 and Q4 are already we have founded the separate groups. So these are the groups we have obtained for the two equivalent. Then the next is three equivalent. So what we are going to do here? In three equivalent, we are only considering the groups of the two equivalent. Forget about the one equivalent and zero equivalent. Okay. So three equivalent. So Q0 and Q2. Q0 on input A, Q1. Q2 on input A, Q1. So Q1 and Q1 means the same symbol. Obviously that will be presenting the one group. So here next is the Q0 on B and Q2 on B. Here it is also Q2 and Q2. Means the same symbol it is, means it should be present in one group. So still Q0 and Q2 are in one group in three equivalent. What about the remaining? They have already separated from the others. Therefore we are writing Q1, Q3 and Q4. So what we can observe here, two equivalent and three equivalent. These two are the same groups representing. Okay. So what does it mean? It means we are stopping to find the equivalency below. When we obtain the same groups, then we can stop finding the equivalent. Okay. So here these are the final states we have obtained. So Q2 and Q0 are combined as a one state, Q1 is another state, Q3 is next state and Q4 as our acceptance state. So here how many states we have obtained? 1, 2, 3 and 4. So how many states are given in our exact DFA? 5 states. Okay. So we have minimized the DFA from 5 state to 4 state. Okay. Now actually we are going to design the diagram for the minimized DFA. So Q0, Q2 as a one state, Q1 is the another state, Q3 and the Q4 which is our acceptance state. So which is initial state? Q0. So we are making arrow of the initial state to the Q0 only. And what about the transitions? That all transitions we are completing by using our transition table. So Q0 on input A, it goes to Q1. Similarly, check for the Q2. Q2 on input A, it goes to Q1 itself. Then Q0 on input B, it goes to Q2. So here Q2 is present. So we are making the loop of symbol B. Q2 on input B, it goes to Q2. Then the next is the Q1 on input A, it goes to Q1. Q1 on input B, it goes to Q3. Then Q3 on input A, it goes to Q1 on input A, and Q3 on input B, it goes to Q4. Q4 on input A, it goes to Q1, and Q4 on input B, it goes to Q2, which is combined with the Q0. So, to that particular diagram, what we have given the name figure minimized DFA. Minimized DFA means whatever the number of states present in original DFA, that states we have minimized and we have obtained our new deterministic finite automata without changing its regular language. So, whatever the language that original DFA contains, the same language my minimized DFA contains. So, these are the steps to solve the problem on the minimization of the finite automata. Thank you, students.